Okay, this is going to be our fifth video in our electric charge and electric fields series here. And so in the previous video we spent some time talking about the electric field outside of a distribution of point charges, right? So we did that dipole example. And then after that we spent some time setting up some ideas that we're going to need to tackle the electric field outside of a charge distribution. Okay, and so we talked a little bit about charge density. We talked about linear, surface, and volume charge densities, and then we went on to do a very brief sort of overview or review of some integral calculus. So we're going to need both of those tools as we tackle the problems in this video. This video is going to consist of basically three examples where we're looking at the electric field at a point somewhere outside of some sort of a uniform charge distribution. So in this first example, we're going to be looking at a uniformly charged rod, so a line segment here with some charge on it. We're then going to look at a ring, and then we're going to look at a disk. Okay, and so the calculations that we're doing are very specific for a certain point, but obviously you could move these things around, and as we'll see, it would change the integrals. In some cases it would make them much harder, in other cases not. But we'll take a look at these three examples and we'll sort of see how it goes, and then we can sort of look at our results, reflect back on them, and talk about how these problems could change. Okay. So as I mentioned, we're going to start off here with this first one where we're looking at a uniformly charged line segment. And so I've taken the time to pre-draw the line segment here. I'm doing this all by hand because I'm not really sure. Well, I thought it would be the best way, and then I'm going to have to sort of do it all by hand because I'm not sure how much space it's going to take for each one. So I'm going to have to maybe pause partway through and then draw another diagram so that we can kind of work with that one. But for this one here, what do we have? We have our uniformly charged rod sitting vertically here on the y-axis, and then we have the x-axis with the origin right in the middle of our uniformly charged rod. So we have the uniformly charged rod extending from minus a, from y equals minus a to y equals a at x equals 0, right? And so we're looking for the electric field at some point P out here, which is in the center of the rod in the y direction, right? It's at y equals 0, but it's out some distance x. Okay. And so how are we going to kind of do this? We're gonna start from one end of the rod and go to the other, and we're going to break the rod up into these tiny little sections, these tiny little dy sections, each of which will carry a charge dq, and we're going to integrate over the entire rod, sort of summing up all these tiny little contributions from the electric field, all these tiny little DEs, to the electric field at point P, right? And so let's sort of get into it and see how this is all going to work, right? So maybe I'll start on the right over here. And so, okay, so we know that we can write the electric field, the magnitude of the electric field at least, as kq over r squared, right? And this is for some point charge. But if we're breaking this thing up into a ton of sort of little infinitesimal point charges, well, then we can sort of write that this infinitesimal contribution to our electric field is going to be equal to k times some infinitesimal chunk of charge over some r squared. Okay. and r squared is going to be changing because we're going to be sort of iterating over the full length of this line, right? So we're going to need to know what r is and how it sort of depends on our y, right? And so r, because r is just the hypotenuse of this triangle here, r is going to change. Well, r is basically defined as x squared plus y squared to the 1/2, right? So it's always going to be the hypotenuse of this triangle that we're creating as we're iterating over the full length of our rod here, right? And so So what is dq? What is this tiny chunk of charge? Well, we need to know the charge density, the linear charge density of this rod. And over here we've sort of written it down. So we know that lambda is the charge density of the rod. This could be a number in a problem, right? Or it could be a function that depends on y. But in this case, this is a uniformly charged rod, so this would just be a number. And so dq is just going to be the charge per unit length times the length. Well, the length here is just dy, right? We're talking about infinitesimal lengths. We're doing an integration over these tiny little dy's. So this is just going to be our dq, right? So for a uniformly charged line segment, our lambda is going to end up being q over whatever our length is, right? So here we have 2a, so it's going to end up being q over 2a, okay? And this means that this altogether means that dq is equal to q, that's a terrible looking q over 2a dy, okay? And we can kind of put this all together to get our infinitesimal contribution to the electric field at P, our dE here. So if we substitute everything in, we end up with a dE that looks like this: k q over 2a dy over x squared plus y squared to the 1/2, right? And so let's take a look. Oh, actually, careful here. So this would be x squared plus y squared to the 1/2, but then we're squaring it, right? We're squaring our r, and so that goes away. Okay. And so let's just take a second to appreciate what we've done here. We started off by knowing what the electric field from a point charge would look like. We're then kind of breaking up our uniformly charged rod into a bunch of tiny contributions, a bunch of infinitesimal contributions to our electric field at the point that we're interested in. We then need to find what r is. We did that. We then need to talk about what dq, this infinitesimal charge contribution is, and that's just our charge density times our length here, right? And so we have to talk about what our charge density is. We do that, and then we can substitute that in for our dq, and then we substitute in dq and r into our original expression for dE. Okay. And so this is good. We're already sort of well on our way to being able to solve this. Now what we need to do is basically integrate this, right? But we can see that we're going to have to break the problem up, right? So we can see that our dE here, our dE at P, is pointing off in the direction a little bit sort of in the I hat direction and a little bit in the negative j hat direction in this case. But we're going to be integrating over the whole line here. So this is going to sort of vary as we move from minus a to a. And so we're going to start off by breaking up dE into its x and y components, right? So let's remember, I'm just going to put some coordinates here. This will be our I hat direction, and this will be our j hat. And again, this is just x and y, right? And so we want to see what dEx and dEy are, right? But we can easily see that from this diagram here, right? We know that if this is alpha, the angle alpha, this will also have to be the angle alpha. And so it's going to have to be true that dEx is equal to dE cos alpha, right? We can see that because it's just going to be the adjacent over the hypotenuse here. And so also we're going to see that dEy is equal to dE sine alpha. Okay, but what are cos alpha and sine alpha? Well, we can easily get that from this side of the triangle, right? Using our sort of mnemonic here, we can see right away that cos alpha is going to be equal to x over r, and sine alpha is going to be equal to y over r. Okay. And so what is this telling us? Well, this is telling us that we can write dEx as dE x over r. That should be an x. And dEy is simply going to be dE y over r. Okay. Okay, so that's great. So let's write out our two infinitesimal contributions to our to our electric field in terms, well, basically the x contribution and the y contribution. Okay, so let me write it out here. Trying to keep this as neat as I can. So we'll move over here now. And so what are we going to end up having? We're going to end up having dEx, and this is just by substitution here. I'm just substituting in for dE what we generated up here, right? And so substituting that in, we're going to end up with k q over 2a, and now we have an additional x over r that we need to consider here, and so we're going to end up with x dy over, and so before we had an r squared in the basement here, we're going to be adding one more r, so this is going to be x squared plus y squared to the 3 over 2, okay? And in the dy direction, oops, that's dEy, we're going to end up with kq over 2a y dy, and again we're going to have an x squared plus y squared to the 3 over 2 in the basement here also, okay? So we've done a bit of work here. Let's keep in mind sort of what it is that we are that we're kind of doing here, right? So what are we doing? We're trying to find E at some point P, right? And we know that we can write E at this point P as EX at that point P in the I hat direction plus EY at that point P in the J hat direction, okay? And how do we get this E? Well, we get this E by, well, our plan here is going to be to get the E by taking the integral of all these individual little dE's, right? And so we're basically breaking up the problem. We're going to break up this vector integral into two scalar integrals that we want to do. And so what do we actually need to do? We need to do an integral where we're going to calculate EX, and that's going to be the integral of dEx, which we just found. And we also want to calculate EY. That's going to be the integral of our dEy. Okay, and this is kind of just an overhead view of what we're doing here. Okay, so I have some stuff worked out here. So let's take a look at this. So I'm going to write out both integrals resulting from these infinitesimal contributions, and then we'll sort of talk about how we're going to tackle these integrals and actually go into doing them. So we're going to want our EY, and the way we're going to get that is we're going to integrate from minus a to a, right? So we're integrating over y here, and on the diagram we can see we have to go from minus a all the way up to a. Excuse me. And so let me write out the integral. We're going to end up integrating this. What are we looking at? Y? Yeah. So we're going to integrate this one here. And so what do we have? We have k q over 2a y dy over x squared plus y squared to the 3 over 2, right? And so we can clean this up. This is going to give us, I'm just going to factor out the things that will pass through the integral, the things that have no y dependence. And so our EY is going to end up looking like this. KQ over 2a, integral from minus a to a, y over x squared plus y squared to the 3 over 2 dy. Okay, and I'm going to call this integral here integral 1. This is one of the integrals we're going to have to tackle in a second. And let's set up the second one. We're going to have an EX. And again, we're still integrating from minus a to a in the y direction. This integral will look like KQ over 2a x dy over x squared plus y squared to the 3 over 2 again. And we can again factor out anything that will just pass through the integral. So we're going to have EX is equal to, again, the same prefactor, KQ 2a, but this time we can factor out the x in the upstairs here, so we're going to end up with an x on the outside. And again, we're going from minus a to a, 1 over x squared plus y squared, 3 over 2. That should look like a 3 over 2 dy. Okay, and this is the second integral that we're going to have to calculate. Okay, so before we move on, let's talk a little bit for a second about what we need here. So basically, we have these two definite integrals that we need to do. We're going to want to change these into indefinite integrals that we can do and then evaluate them at our endpoints, right? This is the sort of fundamental theorem of calculus, and maybe I'll write that down here. Right, so we have integrals that look like this. We're integrating from a to b, sum f of x dx, right? This is what's called a definite integral. And for those of you that have done a bunch of calculus in the past, I kind of apologize for having to go over this, but I mean, everybody's coming at this with different experiences in calculus, and it's a good review for many people. So let's just take a look at it. So this is what we would call a definite integral. Okay, so that's our definite integral, and the fundamental theorem of calculus allows us to relate this to an indefinite integral, which is basically an antiderivative evaluated at 2 points, right? So this is going to end up giving us an indefinite integral evaluated at points A and B, right? And this is what we would think of as an antiderivative. Okay. So let's kind of do this. Let's do this for our, let's say, our first integral that we're looking at here. So let's take a look at 1 here. Okay, so I'm going to label this integral 1. So the integral that we really want to solve in here is, well, the indefinite integral is coming from this number 1 here, right? So what are we really trying to look at? Well, I'm going to call I1 the indefinite integral y over x squared plus y squared 3 over 2 dy. Okay, and so how are we going to solve this integral? Well, the easiest way that I know to solve this integral is to do a substitution here. So we're going to want to do a substitution. So we're going to let u equal x squared plus y squared. Okay, and this means that our du is going to be equal to 2y dy, right? And this means that dy is going to be equal to du over 2y. Okay, and so let's make this substitution. We're going to use all these terms that we've just written down, and this means that our I1 is going to be equal to the integral of, and we can kind of see how we do this here. We're going to end up with still having a y in the upstairs. We're going to substitute in for x squared plus y squared for just a u in the basement here. This will be to the 3 over 2. And then we have our dy. Well, our dy is going to become du over 2y. Oops. And so these y's are going to cancel. And so we're going to end up with, I can factor out this factor of 1/2, right? And we're going to end up with du over u to the 3 over 2. And I find it easier because we're kind of applying the power rule in reverse here to solve this integral, right? So I find it easier to write it as a negative power, so I'm going to write it like this. Right, and at this point we just need to do this integral, and as I said, this is just the power rule in reverse. If any of these ideas are sort of foreign to you guys, I'm not sure exactly how far your Math 112 class will have gotten at this point, but you guys should have already looked at stuff like this, or if you've done Math 112 or something equivalent in the distant past here, just try to remember sort of some of these simple integrals. We definitely need to know how to do the integral of basically the inverse of a power rule pretty easily. So make sure you remember how to do that. And so let's evaluate our integral here. We're going to end up with a minus 2 u to the minus 1/2, right? And this is going to have some unknown constant attached to it, right? And so that's great. So let's maybe I'll rewrite it one more time, clean it up a little bit, and we're going to end up with, so this 2 is going to come outside, they're going to cancel, we're going to end up with a minus sign, and we're going to end up with minus 1 over u to the 1/2 plus c, okay? And so maybe, yeah, okay, I'll rewrite it one more time, substituting back in for what we know u to be. And so we'll have I1 is equal to minus 1 over x squared plus y squared 1/2 plus c, right? And now we're going to use the fundamental theorem of calculus to connect this indefinite integral back to our definite integral. This means that, and maybe fundamental theorem of calculus tells us that the integral from minus a to a y over x squared plus y squared 3 over 2 dy is equal to minus 1 over x squared plus y squared to the 1/2 plus c evaluated from y equals minus a to y equals a. Okay? And we could have saved ourselves a lot of trouble here. We can see, well, hopefully we can see that what's going to happen here is basically this is all going to cancel out, right? We're going to substitute in y equals minus a, it's going to get squared, and we're going to get some term. And then we're going to substitute in y equals a, but y equals minus a, since it's getting squared, is the same as y equals a. So we're going to end up subtracting whatever we get from the top, from the bottom, when they're equal, and we're going to end up getting 0, right? But now, we could have seen right away, and those of us that are maybe a little more familiar with calculus would have thought of this right away. We can see right away that this would have had to be 0, because this function in here, this is what we call an odd function, right? And maybe I can have a space here. I'll add a page. So maybe I'll kind of draw it just here at the bottom. This function would have ended up looking something like this. I think it looks something like that a little bit. Okay, and we're basically integrating this from some minus a to a, right? So this shaded region is going to cancel this shaded region, and we're going to end up with a 0, right? So what does it mean to be an odd function? Well, it means that f of minus x is equal to minus f of x, right? And we can kind of see that here. And because we're integrating over an even region, minus a to a, of this odd function, and that's one of the key components here. You have to make sure that if you're going to set this to 0, that you are integrating from minus a to a, right, over some even region for this odd function. But if you are integrating from over some even region of this odd function, this always has to end up being 0, right? So we could have saved ourselves the trouble, but we can see here that this actually turns out to be 0. So what does this mean? Well, this means that in the end, our electric field contribution in the y direction at point P, maybe I'll put that in at point P, is going to be equal to 0. Does that make sense? Let's take a look at our drawing again. Well, it kind of does make sense, right? Because as we're sort of iterating across the entire rod, we're going to get some contributions that are pointing up, and then as we move further up from negative y, they're going to be pointing less and less up, and then as we hit exactly 0, there is no y contribution, and then as we start moving into positive y values, our electric field is going to be pointing down. If we added all those up, we can see that it's just going to end up being 0, right? So we're going to have no electric field contribution in the y direction. We could have made a sort of symmetry argument about that also. So there were a few ways to make this shorter, but I wanted to do the full-blown problem, so we saw the integral as well. We can see that there's going to be no y contribution, and we could have seen that from symmetry arguments right away in the beginning, or we could have seen that by the fact that we had to integrate an odd function over an even interval, or we could have just actually done the integral like we did and seen that as we evaluate, the whole thing turns into 0, right? But we are definitely going to have an x contribution here, and so let's take a look at integral 2. where we're going to find our x contribution. Okay, so let me, I think I have some stuff worked out here. I do. So let's look at, and maybe what I'll do here is I'm gonna save this PDF to not lose it. So let me pause the video for 1 sec. Okay, so we can now take a look at what I'll call I2, the second integral from equation 2 that we have above. The indefinite integral that we want to solve looks like this. It's going to be x squared plus y squared to the 3 over 2 dy. Okay, and so this one is maybe a tiny bit trickier than the previous one to solve. Again, we're going to want to make a substitution, but in this case we're going to want to make a different substitution. So here we're going to, I'm making a mess of this. Okay, substitution, and so we're gonna let y equal x tan theta, right? And so okay, so this is going to be x tan theta, where we're gonna let theta run from pi over 2, from negative pi over 2, I should say, to pi over 2. Okay, and so what does this mean? This means that our dy is going to be equal to x sec squared theta d theta, right? And so what is this sort of telling us? Well, we're going to need y squared, right? Because we have a y squared in the basement here. So let's sort of manipulate this y substitution a little bit. This means that y squared is equal to x squared tan squared theta, but this means that well, okay, maybe I'll rewrite it like this. This means that we can write the right-hand side of this as x squared sec squared theta minus 1. Okay, and so we can multiply through the x squared. We're going to end up with a minus x squared and move that to the left-hand side, and so we end up with x squared plus y squared is equal to x squared sec squared theta. Okay, and so this is sort of the substitution that we're going to end up wanting to make. Maybe I'll do one more step here. We can take the square root of both sides. We're going to end up with x squared plus y squared to the 1/2 is equal to x sec theta. Okay, and so what does this sort of tell us about dy also? So dy, which we have up here, is going to be x sec squared theta d theta. Now I'm going to multiply through by an x over x here. So basically I can write x over x times x sec squared theta d theta. This is going to be equal to 1 over x squared sec squared theta d theta. And so careful, because we have the same expression up here, right? And so I can rewrite this one more time as I'm squaring this expression up here. So I'm going to end up with an x squared plus y squared, replacing this term here. And so what we end up with is x squared plus y squared over x d theta. Okay, that's our dy. And what we want to do is we want to isolate d theta. So this tells us that d theta is equal to x dy, right? We're just moving. We're basically taking the reciprocal of this and multiplying it through to the left-hand side here. So we're going to end up with x dy over x squared plus y squared. Okay, and so this is telling us that if we wanted to write, well, okay, so one more step here, because what we really want is we want dy over x x squared plus y squared, right? This is what we're sort of trying to get toward over here. So this means that we can write dy over x squared plus y squared is equal to d theta over x. Okay, so we're going to make use of this substitution particularly, and we have this substitution up here that we're going to use. So now looking back at I2, let's substitute some of that stuff in here. Maybe I'll write I2 one more time here. So I2 looks like this, to the 3 over 2 dy. So with our substitutions now we have the indefinite integral, and we're just substituting this first term here, and so we end up with dy. Here, I'll basically write it out. We end up with dy over x squared plus y squared. Okay, so I'm basically just cleaning this up, setting up for our substitution. So what do we have here? I'm pulling out 2 over 2 of this, so we have 1 over 2 left of it. So we're going to have x squared plus y squared to the 1/2 over 1, right? So this is the two things that we want to substitute in for, just to make it super clear what we're doing here. Now we can do our substitution. We're going to end up with the indefinite integral, and this is basically just this term here. So we end up with d theta over x, and this over here is just what we see here. Well, the reciprocal of it, right? So we end up with 1 over x sec theta, right? And so so I can clean this up a little bit. I can write, I can factor out these x's. So we have x squared, and we have d theta over sec theta, right? But we know that sec theta is just 1 over cos theta, so we can rewrite this. And I'm kind of making a mess of this, but we'll just keep going along the same line here. So we can clean this up, and we end up with a 1 over x squared integral cos theta d theta, right? And at this point, it's just a simple matter of doing this integral. We can do that integral, and we end up with a 1 over x squared sine theta plus c, right? And this is good, but we'd really like to be able to write this in terms of our x's, y's, and r's, or I guess our r's, which are the square root of x squared plus y squared, right? Because we're talking about the sort of hypotenuse of this triangle here. So let's try and bring this back into those terms. So we know from our substitution above here that y equals x tan theta. Okay, so let's think about a triangle here. Okay, so y equals x tan theta means that tan theta is equal to y over x, right? But if we're thinking about this like some right angle triangle, if this is a right angle triangle, and this is our x, and this is our y, and this is our theta, and this is our hypotenuse, let's say, then we know that, well, first we know that h is equal to the square root of x squared plus y squared, right? And this tells us that sine theta is equal to the opposite over our hypotenuse, which tells us that y over, well, that it is equal to y over x squared plus y squared, okay? And so why do we want this? Well, we want sine theta because we have sine theta in here, and we can rewrite it in terms of y and x, which are the variables that we're working with, right? So let's make that substitution. We're going to end up with I2 first written in this form, so I'm not going to rewrite it, but we can substitute in for sine theta, and we end up with 1 over x squared, y over the square root x squared plus y squared, plus some constant, right? So this is our indefinite integral, and we now need to bring this back to the definite integral that we want to solve. And so what is this telling us? If we look back at equation 2 up here, we can substitute in for this and evaluate at our two limits of integration here. And let's see what we end up getting. we're going to end up getting a result that looks like, do I have space here? Yeah, it looks like this. So Ex is equal to KQ over 2A, and this is just from equation 2. We have an X, and then we have 1 over X squared. This is our I2 that we're now going to evaluate at minus A and A, right? So we have Y over square root X squared plus Y squared from minus A to A, okay? And so we have this term that we can factor out, right? This is not going to be hitting. Well, this is not going to be affected by the substitution of minus A and A in here. So we can clean this up a little bit, and I'm just going to substitute in A and then minus A at both of these points. Okay, so we can see, what do we end up with? We're going to end up with a KQ, 2A, and now with an X in the basement because one of them's canceled by this X over here. And then as we do our substitutions, we're going to end up with a positive A on top, square root X squared plus A squared, minus a minus A, square root X squared plus A squared. Okay? And so we're really just ending up with, because both of these minus signs cancel, we're just going to be adding them, so we're going to end up with 2, and I'll write it over here. We're going to end up with KQ over, well, I'll do the cancellations here. 2AX, we're going to end up with a 2A square root X squared plus A squared, right? These A's will cancel, these 2's will cancel, and we end up with an expression that looks like this. KQ over X times X squared plus A squared square rooted, right? And so this is great. Let's remember what we've calculated. This is our Ex. This is our X contribution to our electric field point at the point P, right? And this is an important result here, so I'll box it. And so thinking back, sort of what did we end up finding? Well, we ended up finding that our electric field at the point P, I'll drop the argument here, but basically at the point P, our electric field looks like EXI hat plus EYJ hat, right? Except that we found that EY was 0, and so now we can rewrite our electric field at the point P is equal to, and I'll kind of rearrange this a little bit, but basically KQ 1 over X square root X squared plus A squared, pointing in the I hat direction. Okay, so that would be our answer. But before we kind of move on, I want to point out a couple of interesting things about this result. So the first thing is, what do we see? What do we see as we let X get very, very large compared to A? So let me add another page here. So look at X very, very large compared to A. Okay, so in the limit where A goes to 0, basically, right? So what do we end up getting if we send A to 0 here? Well, what would we expect? So let's take a look at our diagram here one more time. What if we're letting X get very, very large? We're letting P float way, way out to the right here. What's going to end up happening to our charged rod? Well, more and more as we get farther and farther, the rod appears to be less and less tall until eventually, when we're very, very far away, it just looks like a point charge to us, right? So we're hoping that in this limit, as we let A go to 0, we're going to retrieve our expression for a point charge. Let's see if we do. So I kind of wrote this way so that we can look at just this factor here, and basically we want to look at the limit as A goes to 0 of 1 over X times X squared plus A squared, all square rooted. And if we take that limit, we're going to find that this goes to a 1 over X squared. Okay, and so what does this mean? Well, this implies that our electric field at the point P, okay, as well, I guess as x goes to infinity, we can think about it, is going to go to kq 1 over x squared I hat, and this, I mean, I guess I can rewrite it in a form that maybe we would see more often. This is going to end up meaning that our electric field at a point P for this setup is going to look like Q over 4 pi epsilon naught x squared, and this is just substituting in our 1 over 4 pi epsilon naught for k, and this looks just like what we would be used to as the point charge, well, as the electric field outside of a point charge, right? So as we get far enough away from this rod begins to turn into a point charge, and as we take it to the limit where we're very, very far from the rod, it appears to be a point charge. There's another interesting limit that we can look at for this one, and then we'll move on. And so what if we let a get very, very long? So what are we sort of doing when we let a get very, very long? Let's kind of scroll back up to our diagram. If we let a get really, really huge, we're kind of, in a sense, letting x get very, very small. We're kind of moving our way up towards an infinitely long charged line segment, right? And so in reality, there are no infinitely long charged line segments, but if we're dealing with a pretty long, say, charged wire or something, and it's very, very long and we're very, very close to it, this result is going to be very, very close to what we're actually going to see as we're sitting very close to that wire, right? So let's take a look at what sort of happens as we get very, very close to this infinite wire, right? So we found, and maybe I'll rewrite the expression that we found here. We found that the electric field at a point P ended up being kq 1 over x square root x squared plus a squared in the I hat direction, right? But now we need to, because we're sort of dealing with an infinite wire, we have to be a little bit careful. We're going to use the fact that that lambda is equal to q over 2a, okay? And we're going to substitute back in for q, okay? So we're going to end up using q is equal to lambda 2a and substitute that back in, okay? So we're going to have well, I'll just rewrite it here. So we're going to end up with k. And so remember, this is, maybe I should have made a note for this. I don't really have space here anymore, but this is going to be as we let a go to infinity, okay? And so we end up with an expression, after we make this q substitution, we're going to end up with an expression that looks like this: 2 lambda a over x square root x squared plus a squared, okay? And so let's kind of clean this up a little bit. I want to start pulling out some a's so that we don't have an a in the upstairs here. And I'm just going to write this to the right here. So what I'm going to do first is I'm going to leave the upstairs the same, and then in the downstairs I'm going to leave this x term the same, but I'm going to factor out an a squared inside. So what does that mean? That I'm basically going to be dividing this by a squared, and this is just going to become a 1, right? So what I've done is just from the term inside the square root, I've just factored out an a squared, but then I can pull out this a squared. It's going to become an a, and they're going to cancel, right? So this is going to cancel with this, okay? And so what do we have to be careful here, because this should still be a vector. And so what do I end up with? I end up with k 2 lambda over x squared over a squared plus 1, okay? And so this is great because now we can kind of easily see what happens as a goes to infinity. So as a goes to infinity, we can see that x squared over a squared goes to 0. And so that means that this term here is going to 0. So we're just going to end up with an x in the basement. So this means that our electric field at some point P, which will be close to an infinite, a rod of infinite length with a charge distribution lambda on it is going to look like this, right? It's going to look like K. We're still going to have this 2 lambda in the upstairs, and that's not an X. That is a lambda. And in the basement, we only have an X left, right? So this is the expression for the electric field at some point outside of an infinitely charged line segment, right? And a line segment that has a charge density of lambda of infinite length, okay? And sometimes we're going to see this written slightly differently, so I'll write it one more time, substituting in for K. So I'm basically substituting in, well, I'll just write it here. I'm going to substitute in 1 over 4 pi epsilon naught for K, and it ends up looking like this. Lambda over 2 pi epsilon naught x I hat, okay? And that's the sort of result for that infinite wire, okay? And so I was intending to, in this video, go on to doing a ring and a disc, and I will do those, but I'm going to do them in a separate video because this video is getting a little bit long, so I'm going to stop here, and I'll see you guys in the next one where we will do the charged ring and the charged disc.